So if you're watching the video, I forgot to record the first part, but that's okay because we're going to be doing more examples of this, so you're jumping in right at the end of this first example. But that's okay, there will be more examples. Or you can go back and look in my YouTube history. I've done this same presentation 4 times, so you can find it somewhere in there. Okay, so we were just looking at this assign u equals y equals e, assign v equals y equals d, or y equals e. This is telling us we have 2 outputs. One of them is u, and u is 1 if our current state is e, and u is 0 if it's not. And v is 1 if our current state is d or e, and 0 if it's not. So it's based just on our current state, so we can put them in our state diagram, and our u is going to equal 1 if you're in state E, and u will equal 0 if you're in state D, and u will equal 0 if you're in state F. Can't really see that on this, but u equals 0, u equals 1, u equals 0, and v equals 0. V equals 1 for states D and E, and v equals 0 for state F. So now our output is uv, and it is 0, 1, 1, 1, and 0, 0. Then I said I was going to change this to a state assigned table, but I changed my mind. We might do that on another one. Okay, so are there any questions on this before we go to another example? Kelvin, any questions?
Not at the moment.
Okay, all right. Well, let me continue then. All right. I'm not, yeah, these are not in the order I want them to be. I am going to go to question 3. And I'm going to repeat some of the stuff I said before because, like I said, I forgot to record. We know this is the verilog code for a finite state machine because we have 2 always blocks. And one of those always blocks appears to be telling us what the next state is. And the other always block is set at the positive edge of the clock, so we know that that's advancing the clock. So in your verilog code, you'll always have 2 always blocks. If you're assigning the output in the first always block, and you're assigning the current output, then that's going to make it a Mealy machine. So this particular finite state machine is a Mealy machine because we're giving the output base. No, we're not. The output I take it back. The output is based on the input, and we'll see why when we get to drawing it. The output is based on the input, so when you see the output is based on input, that means it's a Mealy machine, and you write your output a little differently. So you'll see that as we start to draw it. So how many states does this machine have?
3.
3. You just look at your always block, you see how many it seems to have. It seems to have 3, A, B, and C. So we've got A, B, and C. And what are my directions on this one? What am I supposed to do for it?
It says draw the state diagram of the sequential circuit corresponding to the verilog model.
Okay, so we just need the state diagram. Okay, so we can tell that the variable lowercase y is our current state. And we know that because our case statement in our first always block, this case lowercase y, that variable is always your current state. And then what you're assigning y to be in your second always block right here, when you're saying what y is, this capital Y, where it's coming from, that's going to be your next state. So if you look at what y is becoming, that's going to be the next state. You look in the if statement, what's inside your if, that's your input. So our input is x. And so what does if x, what does that mean?
If x is 1 or 0.
Right.
True or false.
Yeah. And if x right there, that's short for if x equals 1. So if I just have if x, that's short for if x equals 1. So if x equals 1 and I'm in state A, then this tells me my next state is going to be B, and my output, which is R, is going to be 0. Now I write this way. On the arrow, I put the input first, and then a slash, and then the output. And so when you see that on the arrow, the first thing is the input, the second one is the output. And I have to put it on the arrow because I might have different outputs for different inputs. So if x equals 1, then my next state is B and my output is 0. Else, this else means if x equals 0. If x equals 0, my next state is C. So my input is right here, that's 0. And my output is still 0. Now from state B, if my input is, if x is 1 from state B, my next state is C. So I have a 1. And my output is 0. Else, and I'm right here in the code. So this is if x equals 0, my next state is A. And my output is 1. And then from C, I have if x equals 1, my next state is C. And my output is 1. And if x equals 0, my next state is B, and my output is 1. And the if reset n equals 0, that just means if I've pressed the reset button, then the state I'm going to go to is A, so this is going to be reset. And then else y equals y, that's just making it advance the clock. Bye. Did they leave? They can put it in the chat. Yep. Good. Okay, I'm going to stop the Zoom. All right, so I would like you to do question 4 on your own, but I'm going to talk through it up here since I didn't, since the first one's not on here, but you try it on your own.
Okay.
And you just kind of tune me out.
You just want the state diagram for this one?
I don't remember. Did I have directions on it? No, it just says not sure where I got this one. Yeah, let's just do the state diagram.
Okay.
Okay, so I tell that this is a finite state machine because I've got the two always blocks. I see that I'm defining my output outside of both always blocks and that my output depends only on what state I'm in. That tells me this is a Moore machine, which means I'm going to write the output on the states themselves, not on the arrows like I did on the last one. I see I've got 5 states, A, B, C, D, and E. I'm actually going to do this backwards. I'm going to go ahead and look at my output, and I see that my output says Z equals Y equals C or Y equals E. That's equivalent to saying, so Y equals C is 1 whenever Y is C, or whenever your current state is C. And Y equals E is 1 whenever you're in current state E. So this is equivalent to saying Z equals 1 if you're in state C or E, and equals 0 if you're not in state C or E. So I have a 1 is my output for C and E, and it'll be 0 on the others. And then I look at my case statement, and I see if W. So I know W is my input. And if W is the same as saying if W equals 1. So if W equals 1 and I'm in state A, my next state is D. So I will have a 1 right there. Else, the only other thing can be is 0. My next state is B. For B, if W equals 1, my next state is D. Else, my next state is C. For C, if W equals 1, my next state is D. All roads are leading to D. Else, my next state is C. For D, if W equals 1, my next state is E. Else, my next state is B. And for E, if W equals 1, my next state is E. Else, my next state is B. Have a 0 right there. If reset N equals 0, Y equals A, that tells me my reset is right here. And else, it just advances the clock, and that's this for this one.
No, never mind. I see it on the. It's on the second always block that.
Yes.
Reset. Okay.
Yeah. Yeah. But I do want to explain a little bit about if reset N equals 0, Y becomes equal to A. So I I mean, reset in is just a variable like any other variable, but the reason it's called what it's called is you mean it to be active when it's 0. And so we're saying when this variable is 0, that means reset. And so that's why it's called reset in, because you're saying we want to, usually if I had reset, we would probably have if reset equals 1. And so the in is just saying it does what it does when it's at the low value. Okay. All right, and let's go on. And let's see, so I have 5 is a state, another state diagram. And
Sorry.
yeah,
I guess one question I have is, like, how does it know to override with that always block instead of taking whatever cases are going to be used in the first always block?
okay, good question. All right, so first of all, the first always block doesn't actually ever make any changes. Well, it does do the output, but it just says what the next state is going to be. So if you look up at the code up here, we have that output reg r, that is an output, so that is changing right there. But we don't ever go to the next state until we're at the positive edge of a clock. And so nothing happens until you go to the positive edge of a clock. So if this is the basis board, you can be flipping all the switches. Whenever you do, it does the recalculation to figure out what the next state is going to be, but it doesn't change anything until you go to the next edge of the clock. Then, and only then, on the positive edge of the clock or the reset button, when either of those two things happens, if the reset button happens, then when it goes into that, then it'll do this always block. So when the reset button changes, it'll go into this always block, and it'll say, if you press the reset button, the next state is A. And then it'll ignore the else. But if we got here because it's the positive edge of the clock and we didn't press the reset button, it's going to say, it's going to skip this line and go straight to make the next state whatever it is you calculated up here.
I'm sorry, can I get that one more time for the positive edge of the clock?
Okay. This is the key for how this works. So this is the most important thing. So it's the whole two always blocks things. So what actually makes the change is this line right here. That is when you actually go to the next state, because lowercase y is the current state. That's the state that you're in. And so all of this always block, all that's calculating is capital Y, but you don't actually change states. You say what your next state is going to be if you ever get around to going to another state. And you only get around to going to another state when you have a positive edge of a clock. And when you have that, it says, okay, your current state is equal to whatever you calculated it was going to be up in that first always block.
I see. So the block still triggers, but it just disregards that if argument because it's not true.
Right.
Okay.
Right.
I guess that's what's confusing me, because I was thinking like that one of them takes dominance over the other, but
Nah, it's just if the reset button was pressed, then it does that, and if it wasn't pressed, it does the other one.
I see.
And you could have two separate always blocks. You could have always at negative edge reset in. if reset n equals 0, y equals a, that's that block, that's it.
Right.
And you could have the positive edge clock in a separate always block. No, you couldn't. You couldn't. You couldn't do that because you cannot assign the same register value in two different always blocks. So I could not say in one always block what little y is, and then say in another block what it is.
I see.
You have, if I'm gonna, I can say it. I can't. There can't ever. It's kind of like what you were questioning. Is like, how does it know which one to do?
Mm-hmm.
And if I had two different always blocks, there could be the possibility that one would happen
I see.
and mess that up.
Even if you excluded that positive edge clock?
Even so, it's just like it won't let you do it.
I see.
Some compilers will let you, but the Vado will not let you do that.
I see.
Yeah. Okay. Let's do. What time is it?
About 4.
About 4. I think we have time to do both. Let's go ahead and do question 5 because that should be pretty quick now because we have a lot of experience now. And then we'll go back and do question 3, which will take some time. All right, so a state diagram for this one. First, let's determine, do we think this is a mealy or more, and do we know the difference?
This one. He said immediately depends on the, or it takes into account the current state
And current input.
and current input. I'm assuming this one's mealy?
Yeah.
The if argument?
Yep. Well, because the if argument, we're assigning output within the if.
Oh, I see.
Yeah. So what variable is our current state?
That would be lowercase y?
Lowercase y is our current state. What variable is our input?
W.
W. So we know that this variable right here is our current state. Our if is going to be our input. Can you tell what my output is?
Output Z.
Z is my output. And because Z is inside an if that depends on W, we know it's a mealy. So that means you can have different outputs based on different inputs. And we have A, B, and C. And if W is 1 from A, our next state is C, and our output is 0. And if W is 0, our next state is B, and our output is 0. And from B, if W is 1, our next state is C, and our output is 0. And if W is 0, our next state is B, and our output is 1. And from C, if W is 1, our next state is C, and our output is 1. And if W is 0, our next state is B, and our output is 0. And we put those outputs on the arrow because we had different outputs depending on the input. So the first number is the input, the second number is the output. Our second always block tells us that the reset state is A. And were we supposed to do anything? Just a state diagram. Okay, so now let's do the hard one where we have to write the verilog code. It says it's a Mealy type circuit. So I know a couple things that I can start with right away. I do want to do the state diagram first, but we'll just go ahead and do the state diagram, and then I'm not going to do a state table because we don't need to do a state table. State table is useful if you have to do a circuit, if you have to actually like draw out the flip-flops, but not if you only have to do verilog. The only thing to keep in mind is whether or not you have to have a default, and you always should have one anyway, so it doesn't really matter. Okay, so from A, I'm going to C, no matter what the input is, but I have different outputs, so I'll have two different arrows. So I have 0/0/0. So if R equals 0, I go to state C, and my output is 0, 0. If R is 1, I go to state C, but my output is 1, 0. From B, I go to state A if R is 0, and my output is 1, 1. And I go to state C if R is 1 and my output is 1, 0. And from C, I go to B. R equals 0. And my output is 0, 0. And I go to A if R is 1 and my output is 0, 1. Okay, so I'm always going to have a clock. I have R, I have S1, I have S0. And those are my inputs and outputs. So input clock, comma R. Now it's going to be output reg S1, comma S0. If this was a Moore machine, it wouldn't have to be output reg, it could just be output, because with a Moore machine, we assign the output outside of both of the always blocks. So if we go back and look right here, this U and V, those were not reg, those were just this actually does not work. That reg should not be there. This would not work as written.
Oh, okay.
Yeah, so this reg is wrong. I think I remember telling that to the professor. So that could not work, because you can't use the assigned statement with the reg. And a reg has to be inside an always block. But if we look at this one, it is output reg R because we're assigning it inside the always block in question 3. In question 4, we're assigning it outside the always block, and so there's no reg. In number 4.
Yeah.
In number 5, it's inside the always block, so it's output reg. Okay, and then I'm going to have reg Now, how many bits do I need to represent my state?
Would that be 3? Or,
I could use 3, but I'm going to use 2.
okay.
So I have 3 states, so I want to see the smallest power of 2 that's less than 3 is 2, more than 3. 2 squared is 4. So if I had 3, I could do, I could make one of my states 0, 0, 1, one of them 0, 1, 0, and the other one 1, 0, 0. So that is one way to assign states, but I'm going to go with efficiency. I'm going to have reg 1 colon 0 lowercase y comma uppercase y semicolon. And I'm going to have parameter, and I'll have, and you can assign these however you want. 2, except because I have 2 bits, it needs to be a 2-bit binary number. 2 apostrophe B 0 0, B equals 2 apostrophe B 0 1. That should be a comma, not a semicolon. Comma C equals 2 apostrophe B 1 0 semicolon. And then I will do always at lowercase y comma r. So that's going to have both my current state and my input. And this is the format you'll use for any finite state machine. So, doing it, this is the way you'll do anytime you have to do one. So I'm not going to have a begin and end because the only thing I'm going to have in here is a single case statement. And it's going to be case y, because it's always case, the variable for the current state. A colon. And I'm going to be doing several things. So I'm going to have a begin. Actually, I think I only have an if statement, so I don't need a begin. Yeah, I just have an if statement, so I don't need a begin. So if R, but I have more than one thing that I'm going to do with this if R. So I will have a begin. So if R, my next state is going to be, so if when R was 1 and I'm in A, my next state will be C. S0 becomes equal to, well, let me do S1 first because that's the order they're in the table. S1 becomes equal to 0. S0 becomes equal to 0. End. So that was for state A if R equaled 0. I mean, if R equaled 1. Did I do that right? I did not. S1 should have been 1. Else, now I'm going to copy and paste. I do a lot of that in finite state machines. Y equals C, S1. So now, if R equals 0, S1 and S0 are both 0. B, and I do a lot of copy and pasting with finite state machines. So copy all of this and paste it, except it did not all paste. Let me get it all. Okay, from state B, if R equals 1, my next state is C. And if R equals 0, my next state is A. From state B, if R equals 0, both my outputs are 1. And I forgot my end on my else. I forgot to have a begin and end on my else. And now from state B, if R equals 1, S1 is 1, and S0 is 0. And then state C, so I'll copy state B. And from state C, if R equals 0, the next state is B. That's the else. And if R equals 1, the next state is A. That's the if. And for 0, it's 0, 0. That's the else. And for 1, it's 0, 1. That's the if. And now that's the end of my case. So end case. And that's the end of that always block. And then I'll have my next always block, which is going to be always at, and typically when you're writing these yourself, you're not going to have a reset. You can. So if you want to put one in, you can. I'm not going to have a reset on mine because I didn't put that in as an input. So I'm just going to have always at positive edge clock. And I just will have the one line in here. Lowercase y becomes equal to uppercase y. And that's the end. And end module. And now you know how to write verilog for a finite state machine.
I see.
And you just kind of follow that template, and it really makes it easy. It's a the.
Sorry, I was just gonna ask. There's no default with the.
There is so a default. This would be so bad. Yes, we need a default. Default. Y becomes equal to, and you can either set something. I need to have a begin and end here because I'm going to be defining more than one thing. Begin. If I didn't put this in here, Verilog would fuss and say you have a possibility that something's not going to be assigned. Yeah, definitely has to have a default. And what I would have done if I had done this, if I was really doing this for myself, I would have not done this. I would have done this, and I would have had I would have made it vectored rather than two
I see.
separate ones. Okay, any questions?
No, that seems surprisingly, I guess, self-explanatory. Yeah.
It is, and it's like it took me a while to like really understand how useful this is, because if you just make your design a finite state machine and you just figure out what all the possibilities are, then you can do this code and it really goes pretty quick. It seems like it's a lot, but it's really not, because once you have your state diagram, you're just plugging the values in, and with computers, you're not really writing all this, you're just copying and pasting.
Right.
And it works. And so if we had tried to do this like with C++ or something, and you'd have like nested if statements, if this, then this, but you have them it gets messy.
Right.
But this just works.
Yeah, I can see that. Because, I don't know, I guess I'm trying to take, like, whatever I did learn in C++ and try to apply it here, but
You
it's
really
just
don't
not the
want to,
same.
yeah, because the more you try to do that, it's like you'll see when you get your project, you'll think, okay, well, if this is true, then I need to do this, and so you'll start thinking about programming it, and you want to turn your mind away from that and say, no, how do I make these into states?
I see.
And the more you can make them into states, the easier it'll be. You might say, I don't want that many states. I don't want to have 15 states. No, you don't. You'd rather have 5, but you'd rather have 15 states than branching ifs and
Right.
loops all over the place and stuff.
I see. Yeah, because that can get pretty confusing.
Right. Right.
And with this, I guess it's pretty, like, I don't know, descriptive about the actual circuit, if you understand what it's saying.
Right. Yeah, I mean, it does define it. I mean, once you have a state table, you can make the circuit. So I think, is it time? I think I have to, oh, yeah, it's about time for me to shut down
Yeah,
anyway.
no, that's fine.
So, all right.